Hey math fans, welcome to the domain and range of transformed functions notes. So at the top of these notes, I have some pointers on how to tell if a function has a domain or a range, or possibly both, domain and range of all real numbers. And basically that's, can the graph move left and right freely, and can it move up and down freely? If it's yes, either one of those, then the domain would be all real numbers or the range. Another way of thinking about it would be to think about the function itself rather than having to look at the graph and just think, do I have the ability to plug in a positive value? Do I have the ability to plug in negative values? Do I have the ability to plug in zeros? If the answer is yes to all three of those questions, then you have a domain of all real numbers. And that doesn't guarantee you have a range of all real numbers, but it at least helps with the domain part. To ask those questions for the range, you would have to say, like, can it equal a positive number? Can it equal a negative number? Can it equal a zero? That's how you'd figure out if the range has, if the range is all real numbers or not, just by thinking about the function itself. So I always encourage kids to graph it out and look at how the function's moving. Does it have the ability to move up and down or left and right? That usually helps the most when kids are confused. I also included a bit about how to tell if a function has an asymptote. If you're looking at a graph, the graph will curve to avoid touching a value, so it won't pass through that value. Another way of looking at it is you'll get an undefined if you plug that value into the function, so it could show up on the table. The table will say undefined, or the table will approach a limit. A lot of times the table will get smaller and smaller, like closer and closer to zero, but it'll never quite reach it. So you would just look at the number you're approaching and be like, oh, that's where my asymptote is. But other than that, let's get to these examples here. So here I have f of x equals the cube root of x to a of x equals negative cube root of x minus 2 and then plus 5. So first thing I'm going to identify in all my examples in this video is what's the function type. The function type is this. This is a cube root function. So you could say cube root or odd root. Next, I'm going to write a function rule based off of the transformation that happened. So a function rule can be kind of confusing, but basically it is instructions on how the new function was written. So if you think about it like this, you start with your function f of x, and then you transform to your function a of x. So right now, we'll say a of x equals f of x. They'll be the same exact thing. But I am changing the f of x to look like this, right? So how did I change it? I put a negative here, I put a minus 2 here, and I put a plus 5 on the outside there. So I'm going to add that in to my f of x. So this is what I mean. I have that negative on the outside, right? So I'm going to do negative, and then I'll put my f of x, and then I had that minus 2 on the inside. And I know that's on the inside because it's inside of the radical sign here. And then I had that plus 5 on the outside, so that's why I can close those parentheses and just tack on a plus 5 there. So this is my function rule based off of the transformation that happened there. So your function rule will always start with whatever your new function starts with. So that says a of x, so this is going to say a of x. And then it's always going to have f of x in it. Okay? So it'll always have the letter f in it. So function of x. So a of x equals the negative function of x minus 2 plus 5. That's the long explanation of it. Next, we're going to identify the transformations that happened. What happens by putting a negative there, the minus 2 there, and the plus 5. So when in doubt, graph it out. In my earlier videos, I do talk about the definition of, when you have a negative, what happens. But let's just go ahead and look at the graph right here. So in red is my original graph, and then in blue is... So you can see this has been reflected because it's going the opposite way, and you can see that it moved up and to the right. So if I look at this point right here, it goes through 0, 0. that goes 2 spots to the right and 5 spots up. So the -2 that's on the inside goes right 2, and the +5 on the outside goes up 5. And that negative made it reflect, but we need to be specific with how it reflected. Did it reflect over the x-axis or the y-axis? Negatives on the outside of the function, or the outside of the, in this case, the square root, the cube root sign, will reflect over the x-axis. If that negative were inside of the radical here, it would reflect over the y-axis. So I'm going to say reflection over the x-axis. Next, let's look at how these transformations affected our domains and ranges. So if you want longer examples of the domain and range of your original functions, your parent functions, look at the video that precedes this one. But yeah, well, we can go ahead and look at the graph of the cube root of x right here. This graph has a domain of all real numbers because you can take the cube root of any number. You can take the cube root of 0, it's 0. You can take the cube root of any positive number and output a positive value. You can take the cube root of any negative number and it'll output a negative number. So the domain here is all real numbers and the range is all real numbers because the graph has the ability to go up and the ability to go down. Same thing for the domain. It has the ability to go right and the ability to go down. It's not skipping over any values. It's not avoiding any values. It's able to move left and right freely and up and down freely. So when I transform something that is all real numbers, it's still all real numbers. It's moving leftward, it's moving rightward, it's going upward when it's moving left, and it's going in the downward direction when it's going to the right. So it has a range of all real numbers as well as a domain of all real numbers. So I put this on my notes and I skipped over it at the top on purpose because I wanted to point it out now. If a domain or range is already all real numbers, then no transformation will change that. It will always be all real numbers. So that's what I'm going to write for these answers here. I'm going to put them in all real numbers. We're going to write it in interval notation and inequality notation. So you'll notice that I wrote, this is the interval notation, negative infinity to positive infinity, both in parentheses because you can't touch infinities. And then this little e here is like the Greek epsilon symbol. It stands for exists. So this is saying x exists in the set of real numbers, y exists in the set of real numbers. So it's just a symbol you might see sometimes, so I thought I'd include it on these notes. Let's move on to the next example. Okay, so here I have the square root of x transformed to 5 times the square root of negative x plus 3. So I just read this as the square root of x. That's what type of function it is. It's a square root function. If there was a little number in here, it would have to be, and it were odd, it would be an odd root. And if it were a little even number, then it'd be an even root. If there's no number, it's a square root. So you can say square root or even root, but usually we just say square root when there's no little number written right there. So for my function rule, I need to include this 5, the negative inside, and then the plus 3 on the outside. So my function starts with b of x. So b of x will equal, and then how am I transforming f of x? I'm putting a 5 on the outside of f of x. And then, so I'll put my x here. And then there was a negative on the inside where the x is. I know it's on the inside because it's on the inside of the square root sign there, the radical. So I'm going to put my negative on the inside there. So it says 5 times the function of f of negative x. And then the plus 3 is on the outside of the radical, so I'll just tack on the plus 3, and everything's nice and color-coded. But yeah, that's my function rule. So you'll never have like... you'll never have like a power or whatever in it. You'll never have the square root sign in it for this example. You're just writing how is it transformed. And so we transform it by, adding and subtracting values, multiplying values, putting negatives. That's how we make our transformations. So that's all that's going to be in your function rule. Next, let's talk about our transformations. When you multiply by a number greater than 1 on the outside, that's going to vertically stretch it by a factor of 5. When you have a negative on the inside, I mentioned this on the last example, you'll have a y-axis reflection, and then you will go up 3 when you plus 3 on the outside. So I've taken the liberty of graphing it, And so you can see in red is my original, and then in blue is the new one. You see it's gotten taller looking, as if it's been vertically stretched. All right? There's only two ways to get skinnier: vertical stretch or horizontal compression. You know if it's a vertical stretch when the number is multiplied on the outside. If that 5 were multiplied on the inside, like where that negative is, then you would call it a horizontal compression. But the negative on the x makes it reflect across the y-axis, because you can see it was going right, now it's going to the left. And then the plus 3, well, here it looks like it starts at 0, 0, and then it transferred or translated up 3 units. Okay, so when in doubt, graph it out. One more thing I should mention is that whenever you're stating the vertical stretch or compression, you just state the number that it's multiplying by. So this is a vertical stretch by a factor of 5. Whenever it's a horizontal, you flip that factor. So we'll do an example of that in a minute. But let's finish this one. Let's go over the domain and range of the original versus the domain and range of the transformed. So my original in red here, the domain or range is not all real numbers because it starts at 0 and it goes to the right. So that's saying it's going from 0 to infinity. So the two ways you could write it down is in interval notation. You'd have 0 in a bracket because it definitely starts at 0, because you can take the square root of 0. Type in the square root of 0 into a calculator, it tells you the answer is 0. But you can't take the square root of any negative number. So that's why x has to be greater than or equal to 0. So you'd see it written down these two ways: from 0 to infinity, 0's in a bracket, or x is greater than or equal to 0. So let's talk about the transform domain. So the thing that affects the domain on this is that y-axis reflection. Now the graph's going to the left. Yes, it moved up 3, but remember, domain concerns with the x values. So the fact that it went up 3 isn't going to change the domain. Just look at the x-coordinate of this starting point. It's 0, 3. So the x-coordinate is 0. So my domain is still going to start at 0, but it's going to the left forever. It's going towards negative infinity. So technically, it is ending at 0. So you say it's going from negative infinity in parentheses to 0 in a bracket. And then the other way you would represent that is, since it's going leftward now, your sign points to the left. You're saying x is less than or equal to 0. So now let's talk about our range. How's the graph moving up and down? So the original starts at 0 on the y-axis, and then as it's going right, it's going upwards, right? So we still say 0 to infinity. But now this graph has translated up 3 units, and yes, it's been stretched, but the vertical stretch, compressions, all that stuff, the horizontal stretch and compression, that doesn't affect the domain and the range. It more affects the appearance of the graph. But the plus 3 definitely affects the range, because now it's not starting at 0, it's starting at 3 on the y-axis, and then it's still going up forever, okay? So we're going to say the original started at 0, so we're going to say 0 to infinity, and then the new one started at 3, but it's still going up to infinity. So the other way you would see that is y is greater than or equal to 0, or for the new one, y is greater than or equal to 3. So let's move on to the next example. Okay, so here I have f of x equals the absolute value of x to c of x equals 1/4 the absolute value of x minus 5. So what's my function type? It's an absolute value function. What's my function rule? Well, I'm going to start it off with c of x equals, and then we have f of x, right? We're going to write f of x here, but we have 1/4 on the inside of the absolute value bars, so I'm going to put a 1/4 on the inside with the x, so it'll say f of 1/4 x. And then that minus 5 is on the outside of the absolute value bars, so I'll just say minus 5 right there, and that's all there is to it. So now let's talk about what that 1/4 does and what the minus 5 does. So anytime you add or subtract on the outside, it goes up or down that much. So minus 5, it goes down 5. So that 1/4, if you don't know how that's affecting it, go ahead and graph it. And then when you look, the green is the original, the purple is the new one. You see it's gone down 5, but it got wider. So if it got wider, then it's going to either vertically compress or horizontally stretch. So you say horizontal stretch because that 1/4 is on the inside of the absolute value bars. So when I write down horizontal stretch, I need to identify my factor. And I say I have a horizontal stretch by a factor of 4. Why do I say by a factor of 4? Because when we're talking about how the graph looks from the horizontal aspect, it's 4 times wider. We pulled on it to get 4 times wider. So that's why you flip that number when you say the factor for horizontal stretch or compression.
Test, test. Okay, so now let's turn our attention to the domain and range. Um, So my domain of my original is all real numbers. I know that because I can take that, this is an absolute value graph, and I can take the absolute value of any number, any positive or negative number. I can take the absolute value of zero, it's zero. Um, but yeah, if you don't really understand that, then just looking at the graph, you see the graph has the ability to move left and the ability to move right and the ability to pass through zero. I bring up zero because the rational function cannot go through zero. Um, but this can. Okay, so what I'm trying to get across is this domain is all real numbers. So any kind of transformed equation is still going to have a domain of all real numbers. This graph got wider and it shifted down. It's still a domain of all real numbers. So now let's compare our two ranges. Um, the original range, the lowest point, you got to look at range. Can it move freely up and down? The answer to that is no. It can move up, but it can't move down. It has a floor. It can't go below zero. So the original range is y is greater than or equal to zero. Um, and then it translates down five. So that means the new range is y is greater than or equal to negative five because the graph is still going up. So the vertical stretch and stuff, I said this before, that's not going to affect the range or the domain, or horizontal stretch and compression. Okay, that just kind of affects the appearance of the graph and your output values, but it's not really going to affect your domain or your range. So yeah, original y is greater than or equal to zero. The new one, y is greater than or equal to negative five. So this is the other notation of putting the number in the bracket because it does pass through that point, and then it's going up towards positive infinity. So with absolute value ones, you can always look at the y coordinates of the vertex to figure out what the highest or lowest value is. But I'm gonna actually wrap this video up now, and if you'd like to see more examples of this, go ahead and click on part 2. Thanks for watching. Goodbye.